Alright guys, this is try number 2 at this video because it didn't record the sound the first time. Yay! So I'm going to try and remember what I was talking about doing this video. So this is all about spring force. If you have ever played with a spring, you know that as you stretch or compress that spring, it exerts a force on you. So you can feel it kind of pulling back on you or pushing on you. Okay, so that's the force that we are going to talk about today. And this applies to any elastic object, not just springs. So it could also be rubber bands. Sometimes strings are a little bit elastic, you know, things along those lines. All right, so let's say that we had a spring. Okay, when that spring is not stretched or compressed, that is called its rest or natural length. If we were to pull that spring, we would feel a force back toward that rest or natural length. So the spring would be pulling on us. Like I said, that's the equilibrium length or the natural length. Okay. So most of our measurements are going to take place relative to that location, right? And then if we were to compress the spring, we would feel it pushing on us back towards equilibrium. So the spring force is considered to be a restoring force, meaning the spring wants to return to its equilibrium position. So the spring force equation, which we represent with an Fs, is equal to the change in length, okay? Change in length from that natural length. And if you've ever played with a spring, you know that the more that you stretch the spring, the harder it is, or the more that you compress the spring, the harder it is. Now, because the spring force is based on stretch or compression, it is a non-constant force. So what that means is that as we stretch or compress the spring, the force that the spring exerts is changing. Okay, so that F that I drew in those pictures, it's not a constant force F, it's a changing force F dependent upon the spring length. So K is considered to be the spring constant, and that basically tells us how stiff the spring is, and it's measured in newtons per meter. So what that means is how many newtons or how much force would you need to exert to stretch the spring 1 meter. Springs with larger spring constant have a more stiffness. Springs with less stiffness have lower spring constants. So a K of 100 newtons per meter would mean that I would need to apply 100 newtons of force to stretch that spring 1 meter. Okay? And remember that X is the change in length from that natural length. Okay. So on our reference table, you'll notice that there is a negative, and then the force itself is in absolute value bars, and that negative just tells us that the force pulls back toward that equilibrium or natural length. Okay. So most of the time when I'm writing this out as an equation, I ignore the negative and the absolute value bars and just write Fs equals Kx, and I choose the direction positive or negative based on the problem. So another way that we analyze springs is by hanging them vertically. So in the prior problems, we were hanging them horizontally. So when we hang them vertically, we set x equals 0 at the rest or natural length, right, that unstretched length. And then what we'll often do is hang masses from the end and allow the masses to come to rest. Okay, and we say that that rest position is exactly that, the rest position, okay, when the block is at rest. Okay. So when that block is at rest, our net force acting on the block in the vertical direction is going to be 0. So if you think about the forces, we have a force of gravity acting on the block and then a spring force acting on the block. Okay? Now, if our net force is 0, those two forces are going to end up being equal to each other. Okay? So I really have an mg equal to a kx. Now remember, I ignore the absolute value in the negative and I just write in kx. So this would allow me to find x if I didn't know it. This would allow me to find k if I didn't know it. A bunch of different ways to solve for this problem. And now as long as this block is at rest, it will have a net force of 0. Now if I was to displace that block even further, then we would start to accelerate. And this block would end up oscillating back and forth and up and down. And in that case, we would have an Fg minus a spring force equals ma. But the direction of the spring force changes as we oscillate up and down. Once we get past this x equals x point, the spring force is going to change direction. So the spring force will either be in the same direction of gravity or in the opposite direction of gravity. Okay? So since the spring force is constantly changing value and even sometimes changing sign, that also means that the acceleration is going to be changing. So as this block bobs up and down, it has a non-constant net force and a non-constant acceleration. Okay, so what this means is we can't use kind of like our standard kinematics equations to solve for final velocities and things like that. It usually means we have to resort to energy, which we're going to talk about in another video. Okay, but that force is not constant, so it's important to keep in mind. So one thing we often do, or one common experiment that we often do, is we stretch a spring a variety of different lengths. That's what that data table represents. And then we record the force that it takes to stretch those lengths. And when we do that, we end up getting a straight line. And objects that follow that straight line are considered to be Hookean, meaning they follow Hooke's law. And Hooke's law is the equation for the spring force Fs equals Kx. That is Hooke's law. So objects that follow a straight line, when we graph F versus X, like I said, are considered Hookean. So this is going to be like our springs, those sort of things. Now, other objects can start as Hookean, but they might kind of taper off at the end. That's usually like rubber bands and things like that, non-Hookean objects. So they're not following that equation exactly. We are primarily going to deal with objects that follow Hooke's law, or we are going to assume our objects follow Hooke's law. And because of that, if we were to find the slope of that line, keeping in mind that slope is change in y over change in x, it would be Fs over x. And if I look at that equation for spring force, if I divide both sides by x, what I'm left with is k on one side, Fx over the other. So that tells me that the slope of this line is k, or my spring constant. So if I had a bunch of different springs, I could graph F versus X and find their different spring constants. So I think that brings us pretty much to the end of this video. Oh, we got 30 more seconds. Okay. Now, one thing to pay attention to, I forgot I mentioned this, is this spring constant is K and kinetic energy is also K. So I usually write kinetic energy as Ke and spring constant as K, just to avoid any confusion. Yes, on the reference table, kinetic energy is a capital K and spring constant is a lowercase k, but to me there's no difference between an uppercase and a lowercase k, so that's why you'll usually see me write kinetic energy as Ke and not K. That's just to help avoid any confusion on my end. Okay, so make sure you're paying attention to that. Kinetic energy is not the same thing as spring constant. They're very, very, very different things. It's not like you can plug a spring constant in for kinetic energy. So do something to kind of figure out the difference between the two, or to note the difference. Like I said, I do KE for kinetic energy instead of K. That helps me. All right, and that should be the end, and hopefully this has sound.